Dear students, today we are going to discuss about surface chemistry. The surface chemistry covers three aspects: adsorption, colloidal solutions, and catalysis. In the concept of adsorption, first we should be familiar with the terminology that we make use. What is meant by adsorption? It is a surface phenomenon in which two substances come in contact with each other, and the process is heterogeneous in nature. The process of adsorption involves the approach of two substances towards each other. One is called adsorbate, another one is called as adsorbent. Which is adsorbate, which is adsorbent? This concept of adsorption and corresponding terms adsorbate and adsorbent can be compared to a binary solution. A binary solution consists of two components: solute, solvent. Difference is solution is a homogeneous mixture, whereas the process of adsorption is heterogeneous in nature. Solute of solution can be compared to adsorbate involved in the process of adsorption. Solvent can be compared to adsorbent. Hence, in the process of adsorption, adsorbate is a minor component while adsorbent is a major component. Absorption. In this process, one substance penetrates into the inner layers of the other substance. Resultant process is called as absorption. Similarly, one more term also will come across, that is called sorption. If both the process of adsorption and absorption take place simultaneously, the process is known as sorption. The next term is desorption. The process of desorption is applicable for adsorption, absorption as well as sorption. Here the components are separated from each other. Extent of adsorption. It is denoted with the symbol x by m. X corresponds to weight of adsorbate, m corresponds to weight of adsorbate. The ratio between weight of adsorbate and weight of adsorbent is called as extent of adsorption. Generally, mass of adsorbent will be fixed and mass of adsorbate will be varied. Higher the x by m value, higher the process of the adsorption. Types of adsorption. Depending on the forces operating between the components, adsorbate and adsorbent, the process of adsorption is classified into two types: as physical adsorption. This physical adsorption is also called as physiosorption or van der Waals adsorption, because the types of forces operating between adsorbate and adsorbent are physical forces of attraction, which are also called as van der Waals forces of attraction. Hence, this is also called as van der Waals adsorption. If some kind of chemical bond formation takes place between adsorbate and adsorbent, then the process is called chemical adsorption, or it is also called as chemical sorption. Because of the magnitude of attraction forces involved, physical adsorption is always weak in nature and is reversible, whereas chemical adsorption is strong and is irreversible in nature. Factors affecting the process of adsorption. Generally, these factors will influence the process of adsorption. First and foremost factor is nature of adsorbate and adsorbent. Second factor is pressure. Third factor is temperature, and fourth factor is surface area of adsorbent. Now let us see in detail how these factors will affect the process of adsorption. First one, nature of adsorbate and adsorbent. In general, easily liquefiable gases are more adsorbed on the surface of a solid compared to others. The adsorption of a gas on the surface of a solid can be identified by means of a fact called critical temperature, denoted with the symbol Tc. With increase in the critical temperature value of a gas, extent of adsorption always increases. In fact, gases with a higher critical temperature are easily compressible, while the gases with a low critical temperature values are incompressible in nature. Say for example, if you take gases like sulfur dioxide, ammonia, carbon dioxide, which have very high critical temperature values, are adsorbed easily on the surface of solids like activated charcoal, silica gel, etc. Whereas gases like hydrogen and helium, which have very low critical temperature values, are not adsorbed on any surface easily. Effect of pressure on the process of adsorption. The pressure factor is highly effective in case of adsorption involving gases on the surface of solids, and to some extent liquids on the surface of solids. In case of adsorption of gases on the surface of solids with increase in pressure, the extent of adsorption always increases. The relation between pressure and extent of adsorption involving gases on the surface of solids is explained by means of a relation called Freundlich adsorption isotherm. According to this theory, the extent of adsorption of a gas on the surface of a solid is always directly proportional to 1 by nth power of applied pressure, where n is called order of adsorption. Theoretically, the value of n can range anywhere between 0 to 1, but practically the observed values for n are 0.1 to 0.5. When proportionality is replaced with equality, a constant of proportionality comes into picture. This relation x by m is equal to kp power 1 by n is known as Freundlich equation. Its logarithmic form can be represented as log x by m is equal to log k plus 1 by n log p. Graphically, Føllers equation can be represented in the following two ways. Graph can be plotted between extent of adsorption and pressure. Then graph will come like this. If we take the logarithmic parameters, that is log x by m versus log p, a straight line is obtained making an intercept on y axis. This intercept value will be equal to log k and slope of the equation will be equal to 1 by n. By using this graphical method, we can calculate the value of n. In most of the cases, the value of n ranges in between 0.1 to 0.5. In case of adsorption involving liquids on the surface of solids, the Føllers relation is modified as extent of adsorption is directly proportional to c power 1 by n. Here c corresponds to concentration of the liquid component. Generally, it will be solution. Effect of temperature on the process of adsorption. The process of adsorption is always exothermic in nature. Hence, with increase in temperature, the extent of adsorption always decreases. However, it depends on the type of adsorption also. In case of physical adsorption, with increase in temperature, extent of adsorption continuously decreases, whereas in case of chemical adsorption, the extent of adsorption initially increases with increase in temperature, but slowly it will decrease after reaching a peak. The effect of temperature on different types of adsorption is represented graphically like this. In case of physical adsorption, curve will be like this, indicating with increase in temperature, extent of adsorption continuously decreases. Whereas in case of chemical adsorption, the relation between extent of adsorption and temperature can be represented like this. Means up to a specific point, with increase in temperature, extent of adsorption increases. After reaching a saturation point, again extent of adsorption decreases with the increase in temperature. The overall effect is with increase in temperature, extent of adsorption decreases in either case. One more factor affecting the process of adsorption is surface area of adsorbent. With increase in the surface area of adsorbent, the extent of adsorption always increases. Hence, adsorbent is always taken in a finely divided state. In order to keep the surface area clean for the adsorbate to be adsorbed, the adsorbent is always heated in vacuum. The process is known as activation of adsorbent. Catalysis. The functioning of a catalyst is known as catalysis. Catalyst is a substance which alters the rate of reaction without itself changing chemically. A catalyst can be either positive in nature or negative in nature depending on its action. If a catalyst increases the rate of reaction, then it is called as positive catalyst, and if a catalyst decreases the rate of reaction, then it is called as a negative catalyst. As per the requirement, suitable catalyst will be selected for a particular reaction. Further, the efficiency of a catalyst can be either increased or decreased by the addition of some other substance. The substance that increases the efficiency of catalyst is called as catalytic promoter or accelerator. Whereas, if a substance decreases the efficiency of catalyst, then it is called as a catalytic poison or decelerator. As per the requirement, suitable promoter or suitable poison will be selected either to increase the efficiency of catalyst or to decrease the efficiency of catalyst. The characteristic features of a catalyst. A catalyst is highly specific in nature. That means in most of the cases, one particular catalyst can catalyze only one particular reaction. The quantity of catalyst required for a particular reaction is always very much minimum. The catalyst may participate in the reaction, may not participate in the reaction. But at the end of the reaction, the chemical composition of catalyst should remain unchanged. Physical characteristics might change. These are the characteristic features of a catalyst. Types of catalysis. Broadly, the catalysis is classified into 4 types as homogeneous catalysis, heterogeneous catalysis, autocatalysis, and enzymatic catalysis. Homogeneous catalysis. If the reactants and catalyst exist in the same physical state, then it is called as a homogeneous catalysis. Most of the time, homogeneous catalysis is observed in gaseous state and liquid state. For example, carbon monoxide can be oxidized to carbon dioxide in the presence of nitric oxide. In this reaction, the reactants carbon monoxide and oxygen are gases. Catalyst used nitric oxide is also a gas, and in this particular case, the product formed is also in gaseous state. But for a catalysis to be homogeneous, condition is the reactants and catalyst must be in the same physical state. One more such example can be taken is oxidation of sulfur dioxide to sulfur trioxide, again in the presence of nitric oxide as a catalyst. Here also the reactants and catalyst involved are gases. Such catalysis reactions are known as gaseous homogeneous catalysis reactions. Examples of catalysis involving liquids. Esterification is an example involving liquid reactants and liquid catalysts. Acetic acid reacts with ethyl alcohol in the presence of concentrated sulfuric acid to give ethyl acetate and water. In this reaction, the reactants acetic acid, ethyl alcohol exist in liquid state. The catalyst used sulfuric acid also exists in liquid state. In this particular case, the products formed are also in the same physical state. Such catalysis reactions are taken as examples for liquid homogeneous catalysis reactions. Heterogeneous catalysis. The term heterogeneous indicates different physical states. If the reactant and a catalyst differ in their physical states, such catalysis reactions are called as heterogeneous catalysis reactions. Most of the examples that we come across come under the category of heterogeneous catalysis reactions. For example, in Haber's process, nitrogen and hydrogen react with each other to give ammonia. In this reaction, the reactants nitrogen and hydrogen are gases. Product formed ammonia is also a gas. The catalyst used for the reaction is iron, which exists in solid state, and molybdenum or potassium oxide or aluminum oxide, which is used as promoter, also exists in solid state. In this case, the reactants and the catalyst differ in their physical states. Such reactions can be taken as examples for heterogeneous catalysis reactions. One more example that we can take is a reaction involved in contacts process that is used in the manufacturing of sulfuric acid. In contacts process, sulfur dioxide gas is oxidized to get sulfur trioxide. For this reaction, if vanadium pentoxide or platinized asbestos is used as catalyst, then it is an example for heterogeneous catalysis. Autocatalysis. In this, initially no catalyst will be used. One of the product formed in the reaction acts as a catalyst for the rest of the reaction. Such catalysis reactions are called as autocatalysis reactions. These types of reactions are initially slow, but they pick up the speed instantaneously once the autocatalyst is formed in the reaction. Examples for autocatalysis reactions are decomposition of arsine to give arsenic and hydrogen. In this reaction, arsenic formed in the reaction acts as the autocatalyst for the rest of the reaction. Similarly, oxidation of oxalic acid by potassium permanganate is also an example for autocatalysis reaction. In this reaction, MnSO4 manganese sulfate formed in the reaction acts as the autocatalyst. One more such example is the oxidation of more salt by potassium permanganate. In this reaction also, manganese sulfate formed in the reaction acts as an autocatalyst for the rest of the reaction. Enzymatic catalysis reactions. If a reaction is catalyzed by means of enzymes, then it is called as enzymatic catalysis reaction. Enzymes are produced by living organisms, hence these are also known as biocatalysts. Most of the enzymes are proteinous in nature, that is they are made up of essentially amino acids, and these are highly specific in nature. One particular enzyme can catalyze one particular reaction only. That is why the mechanism is also compared to key and lock mechanism. Just like a key can open only one specific lock, one particular enzyme can catalyze only one particular reaction. Chemical reactions involving enzymes come under the category of biochemical reactions. The efficiency of enzymes is dependent on temperature and pH value. Most of the enzymes will have optimum efficiency levels at a temperature of around 37 degrees centigrade, and most of the enzymes will be highly active in acidic environment. So, these two conditions will influence the efficiency of catalyst. In addition to temperature and pH value, presence of metal cations called as coenzymes will also influence the efficiency of enzymes. Coenzymes generally increase the efficiency of enzymes. Some of the drugs and medicines will act as decelerators for enzymes. That is why under medication, biochemical reactions do not take place in a natural manner. Some of the examples for enzymatic catalysis reactions are conversion of sugar to glucose and fructose. Chemically, C12H22O11 is known as sucrose. In common language, it is known as cane sugar. In acidic environment, this cane sugar is converted or hydrolyzed to 1 unit of glucose and 1 unit of fructose in the presence of an enzyme called as invertase. This invertase enzyme is released by a microorganism known as yeast. This process of conversion of sugar into glucose and fructose is known as inversion. Another example is the process of conversion of glucose or fructose into alcohol and carbon dioxide. This reaction takes place in the presence of an enzyme called as 𝗧𝗦𝗔. This 𝗧𝗦𝗔 is also released by same microorganism yeast, and this process is known as fermentation of sugars. Conversion of starch into glucose is also an example for enzymatic catalysis reaction. Starch or carbohydrates are polymers of glucose that can be represented with the general formula C6H10O5 taken n times. These are hydrolyzed to glucose units in the presence of an enzyme called diastase. This diastase is released by malt, germinating seeds. Conversion of proteins into peptides takes place in the presence of an enzyme called as pepsin. This pepsin is released in the stomach by the bile juices of liver, and it is the reaction responsible for digestion of proteinous substances. Similarly, urea is hydrolyzed to ammonia and carbon dioxide in the presence of an enzyme called as urease. This urease is present in soya bean, and this is used for conversion of the fertilizer urea to ammonia. Colloidal solutions. Initially, the solutions that could not pass through semi-permeable membrane were called as colloidal solutions. The name colloidal came from the term colla, meaning glue-like substance. But later, this classification of solutions into different types is done based on the particle size of solute. A binary solution can be represented in the form of mixture of solute and solvent. Depending on the size of solute particle, here size in the sense solute particles, they are supposed to be spherical in shape. So, if we take the radius of solute particle, that is taken as a size of solute. If the radius of solute particle R lies in between 1 micron to 1 millimicron, then the resultant solution was called as a colloidal solution, and this dimension range 1 micron to 1 millimicron is called as a colloidal dimension. 1 micron means 10 power minus 6 meters, 1 millimicron means 10 power minus 9 meters. So, this 10 power minus 6 can be taken as a upper limit, 10 power minus 9 can be taken as a lower limit. If the radius is less than the lower limit, then resultant solution was called as a true solution or molecular solution or ionic solution. If the particle size of solute is more than the upper limit, then the resultant mixture is called as suspension. So, this classification of solutions into three types as colloidal solutions, true solutions and suspensions is based on the particle size of the solute particles. The true solutions, these are homogeneous in nature, while colloidal solutions as well as suspensions are heterogeneous in nature, means different phases are involved or different physical states are involved in the formation of suspension as well as colloidal solutions. Whereas in case of true solutions, only one phase or one physical state can be observed. Classification of colloidal solutions. A colloidal solution in short is called as sol, and the components present in sol are represented as dispersed phase. In short, we call it as dP, and dispersion medium, in short dm. Dispersed phase is just like solute, dispersion medium is just like solvent. That is, dispersed phase is the minor component in the colloidal solution, whereas dispersion medium is a major component in the colloidal solution. Colloidal solutions can be classified either based on the physical state of colloidal solution or physical states of dispersed phase and dispersion medium. That is one way of classification. So, based on the physical state of the colloidal solution, colloidal solutions are classified into three types as solid colloidal solutions, liquid colloidal solutions and gaseous colloidal solutions. If we make use of the physical states of dispersed phase and dispersion medium, then dispersed phase can exist in either solid state, liquid state or gaseous state. Similarly, dispersion medium also can exist in either solid state, liquid state or gaseous state. So, different combinations possible are: a solid can be dissolved in another solid, solid can be dissolved in liquid, solid can be dissolved in gas. Similarly, a liquid can be dissolved in solid, liquid can be dissolved in liquid and a liquid can be dissolved in a gas to get colloidal solution. Similarly, a gas can be dissolved in solid, gas can be dissolved in liquid. The next combination, gas in gas, is ruled out because a colloidal solution has to be always heterogeneous in nature. A gas in gas combination is always homogeneous in nature. Hence, depending on the physical states of dispersed phase and dispersion medium, 8 types of colloidal solutions are possible, which are named based on the physical states of dispersed phase and dispersion medium. If a liquid and a solid combination is there, resultant colloidal solution is called as gel. If both are liquid components, then the resultant colloidal solution is called as emulsion. If gas and solid are involved, the process is known as occlusion. And whenever gas is the dispersion medium and solid or liquid is the dispersed phase, the resultant sol colloidal solution is called as aerosol. These are the various terms that are to be remembered. Another way of classification of colloidal solutions is based on the type of interactive forces operating between the dispersed phase and dispersion medium. If there is no attraction force between the dispersed phase and the dispersion medium, the resultant colloidal solution is called as a 𝗕𝗑𝗍𝗑 sol. Leo refers to dispersion medium, phobic means repulsion with the dispersed phase. Obviously, 𝗕𝗑𝗍𝗑 colloidal solutions are unstable in nature and are irreversible. If strong attraction forces are operating between the dispersed phase and dispersion medium, then resultant colloidal solutions are called as 𝗕𝗑𝗃 colloidal solutions. Here also Leo stands for dispersion medium, philic stands for attraction. So, because of strong attraction forces between the components, 𝗕𝗑𝗃 colloidal solutions are highly stable compared to 𝗕𝗑𝗍𝗑 colloidal solutions, and these are reversible in nature. Another type of classification of colloidal solutions is based on the nature of dispersed phase alone. Accordingly, colloidal solutions are classified into three types as macromolecular colloidal solutions, multimolecular colloidal solutions, and associated colloidal solutions. These associated colloidal solutions are also known as micelles. In case of macromolecular colloidal solutions, the dispersed phase will be in the form of a polymer. So, again polymers are of three types: natural, synthetic, and semi-synthetic. Examples for natural polymers are colloidal solutions prepared by dissolving carbohydrates like starch in water. For synthetic macromolecular colloidal solutions, we can take suspensions of polythene, whereas for semi-synthetic we can take nylon. Multimolecular colloidal solutions are obtained when different types of molecules of the same substance are present in the form of dispersed phase. These types of colloidal solutions are formed when the dispersed phase exhibits the property of allotropy. For example, if we prepare a colloidal solution of sulfur, it may consist of S8 molecules as well as S6 molecules and S2 molecules. So, resultant colloidal solution is called as a multimolecular colloidal solution. Associated or micelles, these exist as true solutions at lower concentrations, and with increase in concentration at a particular level, the dimensions are converted into colloidal dimensions, and from that stage onwards they will act as colloidal solutions. Such colloidal solutions are called as associated colloidal solutions or micelles. One more speciality associated with these micelles is normal colloidal solutions are either 𝗕𝗑𝗃 in nature or 𝗕𝗑𝗍𝗑 in nature, but these micelles will have both 𝗕𝗑𝗃 and 𝗕𝗑𝗍𝗑 ends. In the same particle. One end will act as 𝗕𝗑𝗃 while the other end will act as 𝗕𝗑𝗍𝗑. Best examples for associated colloids or micelles are soaps and detergents. Soap is chemically sodium or potassium salt of fatty acid, which can be represented with the general formula RCOO(Na), where R stands for alkyl group and generally it will be represented with the general formula CnH2n+1. Minimum value of N is 17. If I put 17 in place of N, the resultant soap can be represented as C17H35COO(Na), which is known as sodium stearate. At low concentrations, an aqueous solution of this salt behaves as a true solution, but with increase in concentration and at a particular concentration known as a critical micelle concentration, in short it is represented as a CMC, and at a specific temperature known as a Crafts temperature, denoted with the symbol Tk, the dimensions of soap will increase and reach colloidal range. In that state, the resultant solution is called as micelle. An aqueous solution of soap undergoes ionization as C17H35COO- and Na+. This carboxylate ion part can act as a micelle. The charged end acts as a 𝗂𝗵𝗍𝗫 end, and the alkyl group end acts as a 𝗂𝗵𝗗𝗬𝗃 end. The 𝗂𝗵𝗃 end is strongly attracted towards the dust particles or dirt particles, whereas 𝗂𝗵𝗍𝗫 end is strongly attracted towards water. Hence, as this end is attracted towards water, along with it the alkyl group will move. In turn, the alkyl group is strongly connected with the dirt particles, which also move along with the carboxylate ion. In this way, the dirt or dust is removed from the surface of cloth or surface of skin. This process is known as cleaning action of soap. Preparation of colloidal solutions. Colloidal solutions can be prepared basically by two ways. One process is called aggregation method. Second method is known as disintegration method. In aggregation method, the solute particle size is increased to colloidal dimension. This can be achieved by means of chemical reactions like oxidation, reduction, precipitation, etc. In disintegration methods, the particle size is reduced to colloidal dimensions. It can be achieved both by physical as well as chemical methods. In physical methods, mechanical disintegration methods or electrical disintegration methods are used. The electrical disintegration method is known as Briggs arc method. In this Briggs arc method, the colloidal solution to be prepared, the dispersed phase, is mostly metallic in nature. The metal rods are subjected to electrical discharge in suitable dispersion medium with stabilizing agent. Because of the electrical arc, the metal evaporates and its dimensions will be converted into colloidal dimensions, and in that way if we prepare a colloidal solution, the process is known as electrical disintegration method. By using mechanical dispersion methods or ball mills, we can decrease the size of solute particles to colloidal dimensions. Such preparation method is known as a mechanical disintegration method. Another method of disintegration process is known as peptidization. In this process of peptidization, a suspension is converted into colloidal solution in the presence of a suitable electrolyte. The electrolyte used for the purpose is called as a peptizing agent. Properties of colloidal solutions. The properties of colloidal solutions can be broadly studied under the headings mechanical properties. These are also called as kinetic properties, optical properties, and electrical properties. In mechanical or kinetic properties, we see about movement of colloidal particles. The colloidal particles will be continuously moving without any specific direction, and that directionless movement of colloidal particles is known as Brownian movement. In optical properties, we have to see the color properties and in optical properties we have to see the color properties and scattering properties of colloidal solutions. In electrical properties, we will come across electrophoresis and zeta potential concepts. This zeta potential is also called as electrokinetic potential. And one more property that can be studied for colloidal solutions is colligative properties. Now, let us see one by one. Optical properties of colloidal solutions. Most of the colloidal solutions are colored in nature, and color of the colloidal solution changes with the change in the particle size of the dispersed phase. For the same dispersed phase with the change in size, color changes. It depends on the wavelength scattered by the light. In general, color observed for a colloidal particle is directly proportional to particle size. With increase in particle size, intensity of colors also increases, and it will be towards low energetic end. Another optical property associated with colloidal solutions is scattering of light. When light is passed through a colloidal solution and is observed in perpendicular direction, the scattered light is visible in the form of cones. These cones are called as Tyndall cones, and corresponding effect is called as Tyndall effect. The color of sky and color of water in oceans, seas and rivers is due to scattering of light by the dust particles present in them. Electrical properties of colloidal solutions. Most of the colloidal solutions will carry either of the charge, positive or negative. It is due to the nature of adsorption of specific type of ions on their surface. What type of charge is accumulated by the colloidal solution depends on the medium in which the preparation method is carried out. Same colloidal solution may acquire positive charge in one medium and a negative charge in another medium. The charge is due to preferential adsorption of a specific type of ions on their surfaces. Suppose a colloidal particle attracts positive charge on its surface. Then spontaneously opposite charged particles are attracted towards that first layer. The first layer of ions adsorbed, they are called as a static layer, while the second layer consisting of oppositely charged ions are called as a mobile layer. Between the static layer and mobile layer, a potential difference will arise, which is known as zeta potential, or it is also called as electrokinetic potential. Colligative properties of colloidal solutions. Compared to normal solutions, number of solute particles in colloidal solutions will be less. Hence, the colligative property values magnitude will be less for colloidal solutions compared to true solutions or normal solutions. Specific terms related to colloidal solutions. Electrophoresis, also called as 𝗕𝗏phoresis. Because of the charge accumulated by the colloidal particles in the presence of external electrical field, the colloidal particles will migrate either towards anode or towards cathode depending on the charge present on them. This movement of colloidal particles towards corresponding electrodes is known as electrophoresis or 𝗕𝗏phoresis. This method can be used for the purification of colloidal solutions. So, in this session we have seen what is meant by the process of adsorption related concepts, what is meant by the process of catalysis, types of catalysis, and what is meant by colloidal solution, how to prepare them, how to classify them, and what are their properties.